Dames and Herren, ladies and gentlemen, geehrte colegas, dear colleagues, I hereby formally open this session and I welcome you all to the public defending Mr. Luka Poniatowski. Mr. Luka Poniatowski has presented to the faculty's PhD thesis on the topic Radiation Hydrodynamics of Optically Thick Winds in partial fulfillment of the requirements for the degree of PhD in Science, Astronomy and Astrophysics. We shall now publicly defend this PhD thesis. Mr. Luka Poniatowski, you are invited to give a presentation of 45 minutes about your work. Afterwards, the examination committee will ask questions and discuss the work with you. I will give the floor to Mr. Luka Poniatowski.
Thank you, and I hope everybody can hear me. Welcome today, and to start off, I decided to break down what the title of the presentation means, and throughout the presentation try to explain what are the different parts of this title. First of all, let's start with radiation hydrodynamics. So what radiation hydrodynamics refers to is the study of environments or objects where radiation plays dominant role in dynamics of such environments. An example of such an environment are, for instance, stars. Stars, through the process of nuclear burning, generate light, and light generated by stars can affect the dynamics of stellar gas itself. If generated light is large enough, then star can even start stellar wind. Now there is difference between there is difference between winds here on Earth, which blow or flow along the surface of the planet, and stars from the winds, which blow radially away from the star. In this picture here, the wind will try to blow kite away from the star, while the Mr. K here, or gravity, will try to push or tie the kite back down to the star. And then radiation dynamics will be the study of how this kite flows. The question might be, why stars? And I will have a question to the audience in this case. What do you think? What are more, stars in observable universe or grains of dry sand on Earth? If you think it's stars, please put your hands up. If you think it's dry sand, please put your head on or touch your head. Well, okay, there are mixed responses here. Roughly speaking, there are as many stars as there are dry sands on beaches of Earth. And stars come in all sorts of sizes, colors, and even shapes. For example, here I show sun in this tiny, where's my cursor? In this tiny bright dot here, which you can barely see. And for comparison, I scale artist impressions of several known stars to the size of the sun. And as you can see, some of the stars can be many hundred times larger than the size of the sun. Moreover, what I'm trying to show here is that stars can have different colors. The color of the stars can vary from being deep red to blue. There are also differences there can be stars of different shapes as well. Stars can be spherical, as ones here on the right-hand side, and they can also be distorted due to their rotation, becoming something of a squished shape. Or due to interaction with their companions, they can have teardrop or even in extreme cases, more peanut-like appearance. Out of all the selection of the stars that we have, today I will be focusing on so-called massive stars. So what are the massive stars? Typically, we call massive stars those that are born with initial masses 8 or more times that of the sun. In astronomy, we often as was the case for the size of the stars, like to compare masses and luminosities, or the radiation generated by the stars or outputted by the stars, to that of the sun. Massive stars typically have luminosities that can be million times luminosity of the sun, so they are very luminous. And judging from the first slides, as I said, if light output is large enough, they can drive winds. In fact, massive stars can drive very strong winds and lose as much as 1/1000th of solar mass per year. Not always, but there are cases when this can happen. Through such strong winds and supernova explosions, they can also deposit heavy elements that they produce throughout the process of nuclear burning to a surrounding interstellar medium, thus enriching it. As fun fact, the fluorines commonly present in human teeth was traced back to originate from some of those massive stars. Moving forward, we often, when studying the massive stars or studying the stars, we often study also the life cycle or evolution of stars. Here, diagrammatically, we often present a life cycle of stars as closed circle, where massive stars start their life in star-forming nebulae. In this case, giving birth to O-type star, which then can evolve to become so-called Wolf-Rayet star, which afterwards can undergo supernova, supernova explosion, leaving behind exotic remnants such as neutron stars or black holes, depositing enriched gas into star-forming nebula back, and giving rise to next generations of the star. Now, observationally, it's quite hard to see those stars. They are very far, and they, for us, look like point sources. But what we can do is study how much light they output at given wavelengths or at given colors. Such as studies we call spectroscopy. And here on the left-hand side, I show you example of such spectra, where the top one is characteristic spectra for stars like O stars, where you can see how the light output changes with the wavelengths measured on the x-axis, and the output, the light is measured, or the normalized flux is measured on the y-axis. What is important is that you can see here these very large dips of diminished light output, which we call absorption lines at given frequencies. In contrast, Wolf-Rayet stars are characterized with broad excess of the emission, which we call emission lines. And you can see such example down here, where we have at specific wavelengths, we have very strong emission or added light. Such broad emission lines suggest that Wolf-Rayet stars might have optically thick winds. And since optically thick winds is another part of my title, you might have guessed that today I will be focusing on Wolf-Rayet stars. Before going to Wolf-Rayet stars, there is another way how we can view the evolution of stars. That is to track on so-called Hertzsprung-Russell diagram, where we measure the temperature on the x-axis or the bottom axis, and luminosity of the star on the vertical axis, how the temperature and luminosity of the star changes with time. If we track change of temperature and luminosity, we arrive the pathway that star will take on this diagram, we call the evolutionary track. And here on this example of Hertzsprung-Russell diagram, I show evolutionary tracks for two stars that start their life with same mass, but throughout their life they lose different amounts of mass due to different mass loss. And as you can see, the impact of mass loss on the evolution of the star can be very large. Similarly, presence of companion stars or even amount of metals present in the gas can largely affect the evolutionary pathway of stars. Today, however, I will not be focusing on effects on the evolution, but I will rather be focusing on how or what causes the Wolf-Rayet star, which is here indicated in the circle and product of this blue track, lose its mass. Important point here is that, as you can see, when massive star evolves to become Wolf-Rayet star, it becomes very, very hot. Going to quantifying Wolf-Rayet or explaining what Wolf-Rayet stars are, we can take observed sample of Wolf-Rayet stars and place them on Hirschsprung-Russell diagram according to inferred temperatures and luminosities. And you can see the observed sample in this blue and red marks. As you can see here, on average, indicated by the X mark, although these stars are very hot, they are still not as hot as one would expect from evolution. That would be somewhere where the X mark is beyond even at higher temperatures. So we have discrepancy between what one evolution study would expect, or we would expect from evolutionary tracks to have, and what we observationally infer. This discrepancy in inferred temperature we often refer to as core radius problem. That is because for a given luminosity, the temperature of the star is then proportional, or not proportional, but can be computed according to by the radius. And since we see stars colder than we would expect, it means that observationally we infer stars to be much larger than we would expect from our calculations. Today, I will try to give at least some first insights into what might be solution of this core radius problem. Moving forward, we generally classify Wolf-Rayet stars to be hydrogen-depleted, massive, luminous, and hot stars whose masses lie in range roughly 10 to 30 solar masses, and they have very strong winds with velocities reaching several thousand kilometers per second. Now, what I would like to ask you to remember is these 3 points: that Wolf-Rayet stars are hot, they have strong winds, and that they have optically thick winds. Now, I mentioned this term a couple of times, and I think I should explain what it means. Optically thick wind refers to the situation where so much mass is driven through this wind that wind itself obscures a star from direct observations. So what we see for Wolf-Rayet stars or for optically thick winds, whether it's something else, not Wolf-Rayet star, is wind, but not the star. The question will be then, what do we actually see? And for this, I show you 2 typical observations, different kinds of observations of Wolf-Rayet stars. On the left-hand side here is what we call a light curve, which tracks how the brightness of the star changes in time. Then you may have guessed that brightness is measured here in units of magnitude on the y-axis, and then time in days is tracked on the x-axis. And as you can see, the change in the light output of Wolf-Rayet stars is very, one could say, chaotic, or better say, stochastic. On the other hand, we can also track how the emission line changes, or profile of emission line changes in time. What here on this plot, you can see the average profile of emission lines. This will be the equivalent of frequency, as this will be the how much light do we see at given frequency. And on the top panels here, what you can see is how the excess or decrease of light as compared to the emission changes with the time. And what you can see on these plots here are these stripe-like structures appearing in the observation. So what I will try today is to present you some of the first numerical models, three-dimensional time-dependent numerical models, and I will try to use those models to explain or I will try to compare those models to these observations. So try to reproduce light curves as well as line profile variabilities for such models and see how well we can capture or reproduce properties of Wolf-Rayet stars in the models. Now, since I already mentioned that we only see wind signature, then the fair assumption will be that we need to study the winds of Wolf-Rayet stars. So this will be main goals to understand today's talk, to understand what is the dynamic of outer layers of such winds, of such stars is, and understand what are basic mechanisms behind the winds or driving the winds from those stars. I will then later try to use whatever knowledge we can gain throughout the presentation in order to give first insights to the core radius problem or solution of the core radius problem. So to answer all of this, we need to study radiation hydrodynamics, as title suggests. And going back to Doodles, as at the beginning, radiation hydrodynamic will be study of how the gas parcel, here presented in this orange cube, behaves under influence of the force of gravity and force of light. One tries to, again, pull down gas to the star, another tries to push down away from the star. There also will be the third contribution from other gas parcels giving rise to the gas pressure. Now, mathematically, we describe dynamics of such environments using so-called conservation equations, where the change in momentum, here density times velocity, is caused by the force of gravity, force of radiation, and gradient of the gas pressure acting on the gas. On the other hand, there is conservation of mass, since we are not creating or destroying any mass through this process. Another equation will be conservation of mass conservation, which then will be 0. Moving forward, it's easier to introduce so-called massless rates instead of looking at this conservation equation, and massless rate will describe how much mass flows through the surface, spherical surface around star with a radius r. Similarly to massless rate, it is also convenient to introduce so-called gamma, which will be then the ratio of radiation force to the gravitational force. And as you can see here, this gamma parameter scales with luminosity to the luminosity to mass ratio, as well as this small kappa, which is interaction constant between gas and radiation. Now you might already get first feelings why we are studying massive stars, or why this is important for massive stars, because they have a large luminosity to mass ratio. On the other hand, we still need to understand what the coupling between radiation and gas is. And for that, let's have a look at two different processes with which radiation can interact with gas. One will be radiation interacting with free electrons, and another will be radiation interacting with electrons in a bound states inside the atoms. So let's start off with free electrons. Now, this process is described as so-called Thomson scattering, where a photon can hit electron, scatter it, and change the angle or its frequency. Then, for Thomson scattering, we can compute what is the cross-section of such process, or the interaction constant. And for gas, such as in Wolf-Rayet star, we can work out this number to be approximately 0.2 centimeter square per grams. If we then take characteristic values of luminosity and mass for Wolf-Rayet star, we can also work out that gamma, here indicated with E for the electron scattering, is approximately 0.4. What this means is nearly half of the force of gravity is overcome or is neglected by, not neglected, but overcome by the force of radiation. If we do the same calculation, for instance, for sun, we work out this number to be very, very small. Then this explains why, for instance, sun does not have winds that are driven by the radiation. Okay, now let's move to the other process where photon interacts with the bound state, electron in the bound state, and moves it between two states. For simplicity, we can scale the opacity of such a process to, again, the opacity of radiation interacting with electrons. And then the scaling constant will take care of how efficient this process is, as well as how strong the transition from one state to another state is, and number of electrons that radiation can interact in this specific way, or the number density, here indicated with n. Just to give some rough estimates, let's take or consider such line as Lyman alpha, for which we know that this Q, or the resonance quality, is approximately 10 to the 7, so it's very good resonance. It's quite strong line, and we know roughly what the number density of electrons will be. Number density of hydrogen will be in this case, and estimates that little q, is on the order of 1,000. And scaling back to, or translating back to the gamma, we can estimate that gamma in this case will be on the order of 400. Then you can see that this process is very potent and it can deliver lots of force, causing gas to overcome force of gravity, launching the wind. Now, the important thing here is that there are many of such lines. We only consider tier 1. And the question will be, how do we account for all those in our database that we use 5 million lines? For that, one way will be to take and to assume that gas is not moving, and also assume that radiation and gas are in so-called local thermodynamic equilibrium. Then we can average the effect of all of those lines into so-called Rosland mean opacity and tabulate it as a function of temperature and density. You can see such table from Opal opacity project as a function of temperature on the x-axis and density on the y-axis, given here in the color, in the background color. As you can see, due to the recombination, in this case of iron, many lines are liberated for radiation to interact with, giving very large opacity. Now, if you remember at the beginning, I asked you to remember that Wolf-Rayet stars are hot. In fact, they are somewhere in the region indicated here in red. And as you can see, in this red region, we have quite large opacities, or in this case, I measure in gamma, meaning that radiation, the force of radiation can overcome gravity in this region. As you may guess, this process will be very important in study of the dynamics of Wolf-Rayet winds. However, here we assume that gas doesn't move. But what happens when gas is moving? Well, in this case, I show you this small doodle where I show how the velocity increases, and then I show in the top how lines behave. As velocity increases, lines start to Doppler shift. That means that they move away from their original resonance point. Thus, they can interact with radiation at different frequencies. As this happens, they can absorb more flux than they would in stationary case, giving larger opacity. And to demonstrate this, what I show on the plot here, that will be right hand, is how opal opacity and how this opacity, which takes into account also the Doppler shift effects, change with velocity. Here on the x-axis, you will see the velocity increasing leftwards, no, that's rightwards, and how the opacity changes here. And as you can see, while Rosland's mean opacity or opal opacity doesn't change at all, the other one can increase by a large amount, becoming very important. Again, at the beginning, I asked you to remember that winds of Wolf-Rayet stars are very fast. This means that Doppler effects upon the spectral lines will also be very important in study of such outflows. Unfortunately, there is no general formalism or general tools that we can use in multidimensional time-dependent setup to study these effects. Well, or is there? We set on a quest to at least come up with something, and that something requires some assumptions, which are, firstly, that again we are in local thermodynamic equilibrium, meaning gas and radiation are in equilibrium, but also that within regions where line can interact with radiation, or so-called resonance zones, the properties of the lines and hydrodynamical quantities do not change, that we call often as Sobolev approximation, and that within those regions where the interaction can happen, no two lines overlap. So there are no two lines within those regions. Then we can expand upon our simple one-line scaling to sum over all the lines in our database and get a general kappa. This simple Q then will translate into something that we call force multiplier. And this force multiplier will take into account individual strengths of different spectral lines, as well as how much flux or how much radiation does each line receive, and the optical depth of the line, which in this case will be proportional or inversely proportional to the velocity gradient. So let's try, since we have database, compute what force multipliers are. And we end up with such plots, where what I show you is how the force multiplier changes with the change of this optical depth, little t parameter. As you can see, for very small values of this small t, the force multiplier is nearly constant. It doesn't change, or it's constant, basically. However, after a certain point, it starts to decrease. Luckily, this behavior can be well described by the function which depends on three parameters: q bar, q naught, and alpha. So what do those parameters do? Well, q bar describes what is the maximum value of force multiplier that we can have. Q naught then describes at what optical depths does transition from this flat to this decreasing line happen. And alpha describes what is the slope of such a line, or what is the slope of this decreasing function. What we can do next is to compute all of those three parameters for different temperature and density combinations, similarly how the opal opacities were tabulated. We can then use those tables in our numerical models to best compute what opacity has to be. giving us first tools how to account for these processes in our complicated 3D models. Okay, this covered most background onto what goes into numerical or what goes into radiation hydrodynamics. Next step will be to jump into actual simulations and see how they work. Before that, let me explain you how simulations themselves work. Well, for our simulations, what we do is we assume that the radius, mass, and luminosity of the star are given. We then construct rectangular box starting from the surface of the star and going till certain radius outwards. In this box, to start off, we take simple, less sophisticated or simpler 1D results of simpler 1D model to give so-called initial conditions where we start from. And then we use numerical radiation hydrodynamics code, which radiation part Nicholas Munz, present here, has developed in order to solve equations of radiation hydrodynamics and see how structures or how density, velocity, and other important quantities behave within this numerical box. So without further ado, I will show you one of the first models where what you will see is a video of such simulation where the radius goes diagonally from bottom corner to top left corner, and then the star will be near the bottom right corner. And in color, you will see regions of enhanced density highlighted. Okay, it works. So let's it play a bit, and sorry, go back. No, go back. Okay, what you see here is at the beginning how the initial conditions propagate outwards, and afterwards the flow establishes. And as you can see already from this simulation, is that this flow is first of all very time variable. It changes a lot in time. Secondly, what you can see is that such a flow is not very symmetric. You cannot take one radial ray and say that you can describe everything. So to analyze such simulations, we can also take slices, as shown here in this square, in these rectangles, and see how, for instance, radial velocity changes throughout layer to layer. And what you will see is that even the radial velocity is very structured, and at any given layer you can find regions where regions where we have high radial velocity, regions where we have relatively lower radial velocity, and even in this case, I'm afraid touching. Even in this case, you can see that there are regions of inflow and outflow, positive and negative radial velocity, coexisting at the same radius, meaning that such flows are very turbulent. In fact, our models show the velocity dispersion, which describes more or less the turbulent nature of the outflows, of around 600 kilometers per second. As I already mentioned, these are very time variable and non-spherically symmetric outflows. Furthermore, you can see that outflows are structured. There are many regions of enhanced density, many regions of less of diminished density. However, so-called clumping factor, which describes how does structure compare to the mean density, are quite low, on the order of around 2. To further analyze such models, let's also take average radial velocity, where we average over time and where we average over full lateral directions, and plots this radial velocity as a function of radius. Here you can see it in a solid blue line. As you can see, even on average, it is not very monotonic. It goes up, it goes down. And interestingly, it develops what we call dynamic inflation, a scenario where an extended region of nearly constant density is formed. Why is this important, you will ask? Can you see the gray overlay? It doesn't show on this screen, sorry. Yeah, okay, then you can see it. Great. So why is this important is that having extended region of nearly constant density allows wind to accumulate very large optical depth. And I show the optically thick regions, or regions where we cannot see below in continuum, in this gray overshade. And you can guess that not much is invisible. Everything is hidden behind this curtain of optically thick wind. So let's try and do something that is done in spectroscopy. Takes the parts that we see, which will be now parts in the white, and fit it with assumed velocity law, which in this case will be so-called beta velocity law with exponent of 1, and try to extrapolate down to see where we would think the star, or where we would think star should be, or the stellar radius should be. And what you can see here, doing this fitting starting from the outer boundary and moving all the way inwards, what we find is that our radius is different and it's large. So doing such or following such spectroscopic procedure, we'll again wrong direction. No, again wrong direction. Sorry. Good. Yeah. What we would see is that we are finding stars to be larger. Why is this important? Well, going back to the Hermann-Grasser diagrams that I showed at the very beginning, in order to move this x all the way to this plus all the way to the x, we need radius to increase by around 2.53 times. What do we find? Well, we actually find that we overestimate, if we do spectroscopic fitting, the radius by around 0.5. So you can see how this dynamic inflation can give rise to this problem if we do not account for proper velocity profiles. Next, let's take our numerical models and try to reconstruct pictures of how the stars would look like. And what I'm showing you here, or what I will show you here, will be the movie of how the stellar appearance, temperature, and line profile will change in time as simulation progresses. Here on the top, you will see how, well, stellar appearance. If we were able to resolve Wolf-Rayet stars, what do we think it, or what we think it would look like is shown on these pictures. Here will be in continuum, and here will be at a certain frequency. Does it work? Yes, it works. And what you can see is, firstly, this is very dynamic picture. It changes a lot with the time. Secondly, you already see that star, which here original size of the star is indicated in the black line, looks larger. So visually, such winds make stars look larger. Thirdly, you can see that the temperature or radiation flux temperature changes a lot in time, and that line profiles also change in time. So since we cannot resolve stars, let's focus on those two bottom panels and further analyze those. We can translate the variation of temperature into variation of brightness. And on top, here I show again the observation from from the beginning of the talk. And in the bottom, I show similar light curve obtained from the simulation. Now, you will see, firstly, that the magnitudes or the amplitude of such variations are roughly similar, and that models share similar stochastic nature. However, there is one big difference, that the frequencies or the time scale on which this variation happens are largely different between observations and models. The full span of this model will fit only in that tiny box in the real observation. This suggests us that although we can capture some of the important dynamics, we still need to improve our models. And it can be related to with how we do radiation transfer, how we reconstruct pictures, and how we populate the full volume of the star because we only had small box, or even how often we take the snapshots of such, and how many snapshots we average such behavior. However, importantly, we can reproduce at least some properties of real observations. Next, let's switch to how line profiles behave, because from the small movie, you saw that line profile also changes in time. Here again, on the right, I show you the observation that was at the beginning of the talk, and on the left, I show you scaled to the observation variation of line profile and dynamical spectrum, or how the line profile changes with the time, from the models. Firstly, you can see that in models we do recover these stripe-like structures, and which was not the case. We can even say that the slope of such stripe-like structures, which indicates how the acceleration behaves, are quite similar between models and observations. However, again, there is difference in this case in the amount of flux that such line produces. It seems to be a bit weaker. And again, there is some differences between observations and models. However, the important point is that already at this early stage, models manage to capture some of the important dynamics of such winds. And some differences can be related to what specific star we are modeling, or how we reconstruct our line profiles, or so on. And again, the important message will be 3D time-dependent dynamics matters. And why does it matter? Well, let's assume that, or let's do a small experiment. Take a line computed using this 3D model and compute a synthetic line for outflow which carries the same amount of mass but is smooth and follows so-called beta velocity law. Then what you can see is that those two look very much different. Now, if I assume that this 3D model gives something that is of a real star, or this is actual observation, and I will try to deduce what the mass loss rate and velocity of such wind has to be using this smooth and monotonic assumption. I will underestimate the mass loss rate by quite large factor. I don't remember exactly what the underestimation factor is, but this will be somewhat a large factor. Even factor of 3 will be quite big. So now you can see how or why the time dependency and the multidimensionality matters in study of the winds of Wolf-Rayet stars. This brings me to the conclusions, and I hope throughout the talk I managed to convince you that outer layers of the Wolf-Rayet winds are very dynamic, very structured, and their behavior can only be described in multi-dimensions. Secondly, that the radiation winds, in this case, are driven by the intricate interplay between different kinds of opacity, such as opal opacity or static opacity, and opacity coming from dynamical effects. And I hope you have some initial guesses on what might be the solution to the so-called core radius problem. Although life might seem excellent, we still have things to do, and there are lots of things to do. At the very beginning, I said I'm assuming that radiation and gas are in equilibrium, or in local equilibrium, but that is not very realistic. So we might want to relax that assumption. Furthermore, I use so-called Sobolev approximation, which I introduced earlier, but we know that relaxing this assumption introduces new effects, which are very important for other kinds of winds. Thus, we might want to relax those assumptions. Moreover, although we understand basics, how the momentum is transferred from radiation to gas, we do not understand fully how this process happens. So we might want to invest into more theoretical or more into study of this process. Also, it will be important, or it will be interesting, to take the techniques that I described to you today and apply to study of different objects, such as early type stars, or even disks around stars. With this, I hope I'm on time. I miss a bit, and thank you.
Thank you, Luca, for the very nice and interesting presentation. So before starting with the questions, let me introduce the members of the examination committee. From KU Leuven, we have Jun Sundquist, Hugh Sana, and myself as a chair, Irene Taurino. We also have Alex De Coter and Len Destin, who are today not present, but they are excused. They addressed many questions during the private defense already. From abroad, we have Stanley Owoki from the University of Delaware, Ilek Elmela from the Université Grenoble-Alpes, Kenneth Gailey from the University of Iowa, and Tomer Schenar from the University of Amsterdam. Now, we can start with the questions from people that are online. Professor Owoki? You're muted.
Stan, I think you are muted. Oh.
There we go. Sorry about that. Okay, well, I didn't. We were going to.
Sorry.
Can you hear me?
Yes, we can hear you, but just a second, we cannot see you. Let me try to.
Well, I'm seem to be echoed on the screen as far as I can see.
Okay, we can now see you as well.
Okay, well, I'm not sure that's such a good idea, but anyway. Well, I didn't realize that we were going to have questions from the committee first. I thought there would be questions from the audience. I do have several written down. Let me see if I can go to one of them. Can we go back maybe to slide number 20?
Okay, this becomes a bit challenging now.
Are we allowed to do that? I mean, are we allowed to go back to
slide number 20. Yes, I will try to have either you or slides. Unfortunately, it doesn't work with both for some reason.
I think it's okay.
Okay, I think you should
I
be able to do the slide now.
knew I was going to be on camera.
No. Okay, here.
Okay, so
Yes.
one of the key assumptions is that you can take all these lines and you can sum them up and you get a cumulative effect of those lines. But in the bottom of the 4 points, you say you assume that the lines are not overlapping.
Yes.
And first of all, could you elaborate on what that really means? Overlapping, how close do they have to be? How far apart do they have to be non-overlapping?
So the zones where the photons and lines can interact are defined with so-called they are so-called Doppler resonance zones, and they depend on the velocity gradient as well. They depend on the velocity gradient and the thermal width of the line. So I think in order for lines not to overlap, or to assume that lines are not overlapping, they need to be apart from each other by, I think, 1 thermal width. I might be wrong about that, but that's how I remember it.
Think about it from this point of view. If how fast does the stellar wind compared to that speed, to that thermal speed?
Well,
give me numbers for the thermal speed and for the typical.
Yeah. The thermal speeds in those stars are on the order of 10 to 100, let's say 30 approximately. I don't remember exact numbers, but velocities are then on the order of 1,000. So you get
so if a photon,
100. Sorry?
I'm just saying, if a photon, say you have 2 lines that are within all right, they're bigger than the thermal speed, so maybe 100 or 200 kilometers per second. Does a photon coming out from the star interact with just a single line?
Yeah. If lines are not, so what we are, in this case, we assume that photons will interact only with 1 line. It may interact multiple times with that line, but only once. So the over this 1,000 kilometers velocity spread, there should not be 2 lines for a photon to interact with.
Now you seem to be saying that the separation has to be greater than the wind speed, not the thermal speed.
Okay. Yes, there are two types of overlap. Sorry, I should have been explicit about that. There are 2 types of overlaps that we can think of, or at least I can think of. One is when lines are separated in frequency space not very far within this thermal width, and another when one line can Doppler shift all the way to the resonance zone of another line due to this velocity increase. What we are in this case neglecting both, that no line can Doppler shift all the way to the frequency of another line, which is this separation of several thousand kilometers, and that there are no 2 lines at the same frequency, basically.
Okay, so all right, I don't want to get into this in too much detail. Maybe we go to the private session, but in Wolf-Rayet stars, do you think lines really are, given the amount of mass loss that they have and the momentum, do you think that lines really are not overlapping over the extent of the velocity space of the terminal speed of the wind? Is that a realistic assumption?
That is, it's quite tough to answer that question, because
okay, we can do it in the private section. Okay.
Yeah.
I guess I want to get the point is that, first of all, also, when the photon interacts with the line, does it absorb the photon?
Well, it absorbs and re-emits. We call this process scattering.
Okay. So after it scatters, can it now interact with another line?
well, in principle, it can interact with another line. Under these conditions, no.
Okay. Well, okay. All right. Let's put this off to the private session. But I just wanted to explore this issue of non-overlapping lines with you. Whether that is what level is that assumption and so forth. But I'll let other people now ask questions. Thank you for your answers.
Yep. Thanks for questions.
Thank you, Professor Rovocki. Now is the turn of Dr. Elmela.
Let me again do the trick.
Can you hear me well?
Video inception.
Does this work when I speak? You hear me?
Yes.
Okay.
Yes.
Wonderful. Thanks, and thank you for this great presentation. So, first of all, let me congratulate you, Luka, for this major achievement you've earned by fulfilling this PhD. It's a challenging topic which involves a lot of physical aspects, and I really think you brought convincing answers to long-lasting questions like the core radius problem. So, over the 2 first years of your PhD, when I was still in Leuven, it's been a pleasure to see how quickly you've acquired the main concepts of wind theory and how comfortable you've been juggling with them. So you came up multiple times when we were working together with original ideas to overcome numerical or mathematical obstacles. And I also think that your collaborations with Nico regarding like the numerical aspects and the simulations has been highly beneficial for both of you. It's been a delight to see your overall evolution over the years, and I'm sure you'll keep developing your expertise in Heidelberg. And finally, I'd stress on the careful attention you paid to the analytical aspect of your PhD, and I have no doubt now that you understand the underlying physical mechanisms much better than I do. However, I will try to play my role of committee members and ask you a couple of questions that I didn't have the chance to ask during the private defense. So first of all, like a more open questions concerning the stellar rotation, because I mean stars spin, especially when we deal with massive stars in binary systems or with a companion in a closed orbit where there are tidal interactions. So this kind of stars will also have like a radiation-driven wind, similar to what you described. But how, in your opinion, how will rotation modify the structure of the wind, its launching? How is it going to affect your results? Could you have like a meridional circulation, which will wash out the clumps and the small structures, or is it going to amplify their size, their dimension?
Yeah, thank you for very kind words and also for a nice question. Yes, stars generally rotate, and that was one of the things that I was describing as the reason for stars to change shape. So yeah, there will be 2 effects which stellar rotation can introduce in this case. One will be due to the rapid rotation, due to the Coriolis force, basically, the effective gravity will be reduced. So wind will have easier time to launch at the equators than it will have at the poles. Secondly, what fast rotation does is also it modifies the temperature or luminosity by darkening how they are called, the equators, and brightening the poles. So that will definitely have impact on the wind. And one of the things that can happen is that in this case, whether you attach the simulation box on the equator side or whether you attach on the pole side, since star is not rotating, it's equivalent. So everywhere wind looks more or less similar. But when you have those high rotation, then it will matter whether you're at equator or at pole, because the dynamics will be different. Now, for how it will impact the scale of structures that we see.
Before you mentioned the structures, I mean,
Yeah.
between these 2 effects that you just like described, so like the centrifugal support and the lower amount of UV photons due to a lower temperature at the equatorial in the equatorial plane. Do you have like a gut feeling of what's gonna dominate?
Well, my
I mean,
guess would be
yeah.
that how is it called? Rotational support will force wind to be faster in the equatorial plane. So I think that will be more prominent in this case, but I don't know how much luminosity will be decreased. So it's a bit. No,
Okay, we know that
I think that
we know
winds.
that
Yeah.
yeah, we know that the stars have decretion disk. So I mean, but we don't know yet much about like the formation process of this disk. So maybe, I mean, like that's still a very open question, and I think it would be interesting to try to apply your models to this kind of objects too. Yeah.
Oh, well, but okay. Yeah, sorry.
And so
No,
concerning
I
the
was just
plants, what were
no, I
you?
was just wondering the disks and winds can influence the disks as well. That's I think what you are going to. But even if the star is not itself spinning too fast, and let's take the case when star is not spinning too fast, wind still influences the disk itself. But now, if I understood correctly, your question was what happens to the wind when star is rotating, and I think there are two possibilities. One that it, as you say, either creates a disk or blows faster wind at the equator. Depends what effect is larger.
And concerning the clumpiness aspect?
Concerning the clumpiness, that was one of the future topics that I was mentioning to understand what actually set the size of the structures. We at the moment do not have tools to analyze exactly what sets those structures or the size of those clumps, because we know for some other mechanisms, but not in this case.
Okay. Do you still have time for a small question? Okay, I take the silence as a chair.
One very small.
Okay, very small one. So you explain like that non local thermodynamical equilibrium aspects can be important, especially in the case of blue supergiant and high mass expert binaries. So when you have a tenuous wind, and when the wind temperature and the ionization structure are not related and one-to-one. So you do plan to extend your tabulated line opacity to approximate a non-local thermodynamical equilibrium in the presence of an X-ray ionizing source. So how would you account for the X-ray ionizing source to compute the radiative temperature? And based on the proxy you described in the section 6.2.1 of your PhD manuscript, what's your gut feeling on the impact on the wind's acceleration? Would you be able to reproduce things which have been seen in the literature previously concerning the fact that a moderate amount of X-ray feedback might actually enhance the efficiency of the wind launching?
Okay, just to start at the beginning of what you said, yes, the plan is to extend this approach to also account for non-local thermodynamic equilibrium on NLTE, where the temperatures can deviate from each other. Now, accounting for X-rays is a bit more challenging in that aspect as well. And what's regard... Sorry, I got a bit lost here.
I'm sorry, that wasn't a short question at all.
Yeah. So regarding X-rays, what X-ray can do is ionize your recombined elements further in the wind. And if the case is that your efficiency decreases because you recombine driving elements, then X-rays indeed can, if they ionize them back to higher ionization stages, it can enhance the effect. However, I actually don't know at the moment how that will propagate into the tabulations. It's very hard to predict how this enhancement or addition of X-rays into the tables will behave, will affect so statistical parameters that we tabulate.
Yeah, I agree. That's a challenging task, but I hope you find the time to overcome it. Thank you for your answers.
Okay, we can go ahead with Professor Gailey.
Can you
You are
unmute it, I
mute.
guess?
You are mute.
Sorry, I forgot about that. Yeah, nice job describing a lot of really detailed physics, and you really focused a lot on the clumping and the inhomogeneities, because that's what you can do that is really in 3D. That's just not really available for most people. But I also want to stress the fact that there are fundamental questions about Wolf-Rayet winds that are unanswered, even in the context of smooth winds. So, like basically, how do you drive them? They're very high mass loss rates, and it's not really all that clear how you drive them. So let me just ask some general questions about that I think your research has a lot to say about. So one is that, we hear a lot about light carrying heat and energy around in astronomy, but we rarely talk about light pushing on things. So why is that true? Why is it so much less the case that we worry about light pushing on gas instead of just carrying energy around?
Thank you. It's quite interesting, deep physics question, basically. The reason why we care about light carrying energy, but less light pushing on things, is related to how much energy can a photon carry versus how much momentum can photon carry. And the ratio between energies that photon can carry and momentum that photon can carry is basically the speed of light. Speed of light is a large number, and for momentum, it plays inverse role. It decreases the amount of momentum each photon carries. So you need to have a lot of photons in order to have meaningful momentum transfer versus meaningful energy transfer. So I think the reason is that for massive stars, we have lots of photons. They are very luminous. Versus, for instance, for sun, although radiation sets energy balance, and it's important in carrying the heat in the sun, or especially outer layers, it is less luminous. It just does not have that many photons for this momentum transfer to be important.
Okay, thanks. So you mentioned the sun. So the sun, for the reasons you described, the sun wind, which is very weak, is not thought to be driven by its light. It's thought to be driven by its own gas pressure, which has an interesting characteristic that if you dump more energy in, you just increase the gas pressure, and you can really drive as much mass as you want based on how much energy you dump in. Yeah. Why is that not the case in these massive stars? What's different about them that means that they can self-regulate their mass flux?
Yeah, that's an interesting problem. As you say, in sun, the force that is supporting the outflow comes from the temperature or the gas pressure. And as you say, more you have, more you can drive. And then, simply speaking, the equation of motion can become independent of the density. However, in massive stars, the radiation force itself depends on the density. So there is fine balance between the velocity and the density structures that those winds can have. If you have too little density, so you are somehow choking the wind, the radiation force will try to increase the velocity, creating some kind of vacuum that tries to suck more and more density out, increasing the mass flux and density in the wind itself. And vice versa, if you have too much density, such wind cannot be driven, and velocity will start to decrease, trying to decrease the loss rate before it settles down to something, or even stops and reignites some other structured outflow. So this interplay between velocity and densities and gives the self-regulations that comes from the dependency of radiation force, the line acceleration in this case on the density and velocity itself.
Okay, thanks. So you're saying basically that this interesting interplay between velocity gradient and density kind of giveth and it taketh away. It giveth a simple way to understand how these stars regulate their mass flux, but it also creates all kinds of weird and dynamical effects which you're studying. So in a way, you're able to study both at the same time and understand how the wind gets driven at all at the same time as you're understanding the extreme level of complexity and structure in the wind. Okay, I understand. Thank you. That's all I had.
Okay, thank you. So now we can go to the questions from the members of the examination committee who are here present. So Professor Sana, or okay, Dr. Shenar.
Probably you need to give a microphone.
Yeah, sure.
Thanks. Where should I stand? Here? Or doesn't matter.
You either smile to that camera or smile to this camera.
Okay, Luka, congratulations. First of all, I won't repeat all the compliments that you heard from Ilek, but I can repeat them in my head. I have two brief questions. I'll try. I think they will be very quick because you'll know immediately the answer. The first one, you described nicely how efficient line transitions are in driving the wind, right? And especially elements like iron are very good at that. They have a high opacity. But the stars that you're talking about comprise primarily hydrogen and helium. So how come we do, right? Or am I wrong?
For Wolf-Rayet stars, as I started at the beginning, they primarily helium.
Okay, primarily helium. So why don't we see a wind of iron being driven out? Like why is the helium also being driven out and not just the iron?
So you are depositing momentum to certain ions, but basically you can also ask why don't we see only the charged particles, ions, being driven out, but the plasma is neutral. Firstly, the moving ions drag along the electrons as well, but they can also redistribute momentum through the heat processes, the collisions to other ions as well. Yeah, you are primarily dumping energy into, or kinetic energy and the momentum into certain types of ions, but they can redistribute that into other elements as well, dragging or pushing others out. Thus, you are driving not only, and also not only iron lines experience acceleration, but other elements also have lines which will also experience acceleration.
Okay, fair enough. A second question, it's interesting to test these models, right? The models that you produced in collaboration with Nico as well. And one of the interesting things that you showed is that there are some regions in these models, if you take these cross sections, where the wind or the material is actually infalling. And I wanted to ask you if you can think of any observational way of testing this.
Honestly speaking, it will be very challenging for observational probing of that, because what we see is that processes mostly happen in the optically thick regions, so that we cannot observe. We see imprints in, for instance, stochastic nature of variability. The turbulence makes everything stochastic or random, more or less. So we may probably see imprints in this stochastic nature, but not direct observation, or at least I cannot think of direct way how to see infalling parcels of gas, since they are, again, in the very optically thick regions.
Okay, that's comfortable for modelers to not be able. Thank you.
Okay, one small question, Professor Sana. if possible. One.
Only one. Two.
Well,
we negotiate two. Okay, last three. Um, so I was quite pleased to see that between the private defense and the final version, the number of times you mentioned binary has been increased by a factor 10.
I was shooting for something like factor of 4, but
Well,
I overshot it.
I mean, you've been using synonyms like multiple stars and that kind of things. Anyway, page 6, you write, and that has intrigued me, you write that the fact that the binary fraction of Wolf-Rayet stars across the galaxy, the small massive cloud and the large massive cloud, which is about 30–40%, that doesn't change then. This might indicate that multiplicity is not the dominant formation channel at low metallicity. And I did not understand the reasoning between that argument.
I also need to think why the argument holds. So I may ask author of the paper, Tomer, can you help me out?
No, you're not allowed to call for a friend.
Oh, no. I hope for the friend cover. Well, I think that's related to how does binary fraction change of early type stars across the
There's metallicity, it's constant.
various metallicity, that's constant. Okay.
Okay, we'll discuss that later. I don't have much time, so let's move to the final sentence of that paragraph, where you write that in this work you only consider non-interacting or single Wolf-Rayet stars.
Yes.
And I was wondering why. Does the physics that you have been considering does not apply to binary stars?
Well,
or are you thinking about different physics in single stars and binaries?
In order to model, if we have binaries that are interacting, then you need to account for the effects of binary companion onto the wind as well. It can modify the gravitational potential. It can create all sorts of things. If it's very close, it can start to accrete the gas that is emitted from one star onto another star, or other star also has luminosity. The wind can experience radiation force from the other star as well. So then you need to study what force you have from one side, what force you have from the other side, which makes everything a bit more complicated to study than single star.
But the tools that you developed have probably been the first to actually allow that kind of simulation in 3 dimensions, realistically.
Well, basically, yes. You just need more complex scenario to set up, not just a simple box with one source of gravity.
So I hope that at least you or one of your colleagues will try to do those binaries at some in the near future. Because when we were discussing an object recently, I think that new simulations or new tools would be a great addition to model those systems, and we will be able to have been underestimating the mass loss by fitting 1D model to particularly thin winds. Is the difference between 1D, 3D that would you expect that the difference between 1D and 3D in optically thin stars be of similar order of magnitude or not?
If that will be on the similar order of magnitude, let me think why it might not be on the similar order of magnitude. Well, in Wolf-Rayet stars, what we now have is emission lines coming from the winds.
Yeah, in O stars too.
In O stars, you have P-signaling lines.
Or we can have lines fully in emission, like for helium-24686 or H-alpha. The combination lines in supergiants will be in emission.
I would bet that, well, I would guess that 3D effects will still be important. I don't know whether it will be on the order of 3 or 4 times, or I don't remember exactly what the number is. But again, 3D effects will be important because your
in
wind
one of
will
your
not
first
be.
slides, you show how important it was factor 3 in the evolution.
Sorry?
You show in one of your first slides how important factor 3 was on the evolution, even in the mean sequence. And the model predicts lower mass loss rate, but we would like to see whether the 3D interpretation that we've been fitting is also a factor.
Yeah, I understand where you're coming from, because we also have this theoretical discrepancies between predicted mass loss rates from different recipes, so-called.
I think the chair is looking at me very angry, so I'm handing over.
Yeah.
Thank you.
Okay.
Yes, sure. So anybody from the audience has a question for Luka? Do you need a microphone? You can try to speak if... okay. Otherwise...
Hi, this is Don Bowman. Thank you, Luka. That was really, really nice talk. And first, let me compliment you on the talk, but second, compliment you on having such a large jury. That is not an easy task, and you handled it excellently. My question, so I think it was slide 29, but you don't have to bring it up, so it's fine. You had your plus and your cross, and you explained why your Wolf-Rayet sample is observed to be the right of the helium main sequence, but there were stars to the left of the helium main sequence. Why are they there?
Well, so those stars can be so how the temperatures are estimated for those stars is that you have you assume some kind of velocity law, as I explained, and you try to extrapolate it down to certain optical depth. And depending how you use it, what kind of scenario you have, you might end up having large temperatures. It's not possible through those methods to have stars that are hot. It's just that in overwhelming majority of the cases, we find stars that, or the stars are inferred to be colder than what we would expect.
Okay, so are those more observationally challenging, as I would understand?
I don't know individual stars to give you answer whether it's of observational challenges or just models work particularly well for those stars. I don't know exact details of those stars, but again, it's a lower limit that we are interested in, not the upper one in this case.
Okay, excellent, thanks.
A couple of more questions. So if anybody has...
Thank you, Luka.
Hello, Florian.
Hi. So I had a very basic question I think might be interesting for the audience. So you showed a few times photometric spectra from the observations and you compared them with your model. But you always said that they were stochastic in origin and not chaotic. So what properties that you see, why do you classify them as stochastic instead of chaotic? What is the defining property?
You are trying to fail me now.
No, it was not at all.
Well, I don't remember exact definition. What's the difference between stochasticity and chaotic? What we mean is that the trend in changes is more or less unpredictable, but it follows some it does not just randomly jump up and down. So it's not a random distribution. It is stochastic in nature, meaning that there is some kind of continuity in that, but not the trend that we can fit with some periodic function.
So did you look also at other like power spectra, or to find
what do
so
you mean,
from
power
your
spectra?
so from your simulations, did you look at like power spectra, something to learn more about this
Yes.
stochastic
Well,
property then?
So stochastic properties, well, if I think Dom is better to answer that question, but you can compute what power and what frequency, or you can decompose that into different frequencies and see what amount of power at every frequency you find. And that is one of the measures that they do in study of the stochastic nature of those variables. Yes, I have done preliminary analysis. Well, not analysis, but I at least have power spectrum. And there are some similarities, but again, the difference in the time scale gives you very large difference in the frequency space. So everything is shifted towards time scales are smaller, higher frequencies. And
Okay, thank you.
I can allow only one more question. So if somebody, no, good. So now the members
with question part at least.
The members of the extension committee will retire for the final deliberation. Ladies and gentlemen, dear colleagues, I will now proclaim the results of the deliberation by the examination committee appointed for the doctoral degree in science, astronomy, and astrophysics. Mr. Luka Poniatowski has presented to the faculty his PhD thesis on the topic Radiation Hydrodynamics of Optically Thick Winds in partial fulfillment of the requirements for the PhD in science, astronomy, and astrophysics, and he has defended his thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of the rector of KU Leuven, I confer upon Mr. Luka Poniatowski the degree of Doctor in Science, Astronomy, and Astrophysics, and I close the session. Congratulations, Luka. So now I give the word to Yun.
Take off my hat for you, Luka. Yes. All right. So, okay, I'll be brief, like I always is. Might take a while. Well, it's done now, Luka. You can relax, breathe, and yeah, it's been it's been quite some 4 years or so, I must say. But I was a little bit. I saw in your, I don't know if you told me or if it was in your acknowledgement, actually, you said something like, it might not have been the smoothest journey, but actually I thought it was very smooth, at least for me. So I'm not really sure what you were referring to there, but then I actually, okay, I did start to look back when I read those words, and perhaps you're true that it was not always the smoothest. It was an excellent journey. I think you don't have to tell you so much about that, although I might. But yeah, first, of course, I mean, even to obtain this position, you had to go through basically a veil of ignorance from your to-be supervisor, which was not easy, because I remember who was also there during the interview, and we had these excellent candidates. Everybody, of course, agreed that Luka should have the interview. Then Luka started to talk, and I was like, man, okay, what is this? Luka knows this. We have been making a lot of jokes, because I thought that this guy was from Georgia. Yeah, he is, they said. Oh, okay, it's not the state. So that's what I said, veil of ignorance with the from the supervisor. So for that reason, I got you a first thing, just to show you that really grown in my love for Georgia. So the first will be this one. For you, Luka. Here you go. Yeah. Yeah. Yes. So, did I do it again? Okay. Anyway, it has not been easy for you to have to wade through all of that. And then, of course, yeah, it took a while before you arrived. And then you did arrive. But yeah, perhaps that was also not easy. I do remember that there were some talks at the institute when you came, that there was some random guy in some Facebook group asking very specific questions about chemicals. So I think that there was a lot of people who got a little bit afraid there. It turned out that it was just that you're very good with drain cleaners. I come to understood. Okay, yeah. Actually, Luka is, and a lot of people at the institute, yeah, he's quite a handyman, actually. He also put up the board, the whiteboard in my apartment. Very nice. It's just like I moved now, so now it's still in my corridor. just to let you know, yeah. Yeah, I got it down, but now I don't get it up again. I still don't know how you did it. And this is actually true. So he is quite a handyman as well. He has a lot of these, yeah. And then, of course, there was the whole apartment thing. It's all quite famous, I think, among the audience. You know, you moved here only to find yourself in a very, very tiny apartment. People know this, and he was famous. And then he got a bigger one. But then I think you had problems with bed bugs. And it wasn't really so big, that one either. And now you finally got a new, very nice apartment, yeah. And now you're moving. It has not been easy life for Luka. So we better go to science there, because there it was very easy. A smooth journey. And actually, we have heard it from many, but Luka has done some really amazing work during these 4, and actually done some really breakthrough modeling tools for our field, which I'm pretty sure they will be extremely useful for quite a long time. And I think this is also starting to show in terms of merits, in terms of you have your new positions, people are emailing you, asking you about your tools, or being upset with us because we don't cite them properly. That can also be the case sometimes, as you know. But another thing, of course, with Luka is that he's extremely helpful and kind. And did I lose that? Did you steal it? Oh, I had it there. Yeah, he's actually extremely helpful and kind, and he's a lot, you all know. And it was very surprising to see that he actually put this figure as his profile for the first year or so. I don't know if you remember this, but yeah, I really don't know. But this is not the Luka that we know, you know. He smiles like he does now, so I think this one is indeed much better, huh? Yeah.
I remember where the photo came from.
Yes.
Small story. It's the middle of night. I remember sending email from Theo. I didn't know who Theo was at that point, asking me to put. Oh, my was not on. Is it on now? Yeah. So, small story. It was 4 years ago now. I received email late at night, or at least I saw late at night, from Clio telling me that I need profile picture, otherwise they cannot proceed with creating my account. And by that time, I'm already 6 months late to start my PhD. So you see that email and you immediately act. You don't wait 5 more minutes, because that's delay of 5 more months. So that picture is actually taken at my headboard, my bed, where I just put on first shirt I could find and took with my, at that point, 10-year-old laptop. I was very happy to do that midnight. So
yeah, there you go. But you've done a great job since, because I Googled it. I tried to find it yesterday, and it's magically vanished. When you Google Luka Poniatowski, it does not appear. Very strange. How did you do that? You're going to have to teach me some stuff in terms of that as well. Huh? But we can come back to that. Yeah. Now, what I said was that actually Luka, he is more like the second, because he's extremely kind, also extremely helpful to everybody, and not the least the students in our group. In fact, he's so helpful that he has been supervising a master thesis, right until, well, basically last week, while preparing his defense. And in order to prepare the master thesis presentation, you offered to have a meeting to prepare that, even after you have done this, right? It's just, I saw it in my calendar, and you had put it for 3 a.m. this morning at Audemarkt. I don't know. I don't know, Luca. That's I'm on diaper duty then, so I cannot come. But you can have it there.
Yeah. We have special corners there with all the required glasses
perfect. And actually, then you can also perhaps solve one thing which is actually missing from your time here, because Luca and I have also been teaching together for more than 3 years, and he has compiled this really amazing set of solutions to our radiative processes course, to all my notes where I put down the exercises, but I don't know the solutions, so Luca solved them for me. And then he has compiled them, but there is actually one missing, and that's the random walk exercise. So one of the things we teach is how diffusion of photons, so radiative diffusions, can be modeled as a random walk or a drunken walk, as we call it in the class. So essentially, the one of the examples we have is that we take the distance between Audemarkt and the classroom, and then you can do a random walk there, but then you can say, okay, that's just the distance. It's actually a two-dimensional problem. So you may miss the classroom, and that might then explain the gradient that we see between Wednesday afternoon class and Friday morning class. But there is no solution to that in the compendium, so perhaps that's what you're aiming for.
Yeah, the idea was I track on my phone.
Then really
how I reach meeting.
Your set would be truly complete. So yeah. So I realize now that I talked a lot about other things, but not so much about the science. But that's also because, like I said, I think it speaks for itself, how good it is, and just really on how high level it is. And also in terms of what we have been doing together and in the group and with our colleagues here, and also with colleagues on StreamYard there. But one of the things is also that I truly hope, and I believe that this is just the beginning. Because like I mentioned, now you're, of course, already moving to Germany to start a postdoc life, away from me, away from us here, being independent. And then, of course, I've already said that, okay, but I will save money for you. So in 2 years, you need to come back to me here. So you already have that. So you know. So that's essentially how much I believe in Luka, that, yeah, okay, but you can come back, huh? Unless, of course, you find something better. But then again, what would that be? But yes, then to finalize this, today I'm actually amazingly proud of you, of our team, and the work that we've been doing together for 4 years. And like I said, I really hope and I believe that it will continue. And now when you go into Andreas, you will hear a new voice, and it will be perhaps not as annoying as mine, but you know, probably pretty as well. So between the time in Heidelberg and perhaps if you come back here, if you just feel at some point that it's too much, I want you to know that that's also okay, Luka. There's always another thing that you can always do. So that brings me to my next thing, right? So that will be the final, the second with. If you ever get too tired of it, then you know what to do.
This is a backup plan.
But I'm sure you will. I actually brought my own bow tie. I figured that you will have. So I will now take your lead. You're going to have to educate me because I don't know how to tie this one. So you're going to have to do that for me. And then, yeah, congratulations, Luka.
Thank you.
It's been a real pleasure. A real pleasure.
Thank you. Thank you. Yeah, sure.
Now we can be alive. Look at that. Perfect.
Nice.
No.
Thank you, and thanks everybody. In my acknowledgements, I wrote that it's probably toughest part, and I still stand by my words. I was probably supposed to prepare something, but I will try to go impromptu. All the adventures that Jon talked about were amazing, but I think the most amazing part of these 4 years was to come and see these amazing people who became my friends, my supervisor. I know it's tough to be friends with me and supervise me. So after 4 years, I thought that this will be of use for Yun. And, well, it comes with the second part. I hope that you would open that. But first you can open this one and try to guess what that is. So after 4 years, that will be very helpful, especially after knowing me and working with me nearly every day, all day. So that is a drinking horn, which is very traditional at home, and that is beginner size. So as we progress, I can upgrade to larger and larger. You're welcome, Jim. I have many thanks to say to you. It's been a fantastic journey, and I learned a lot. I started with completely different topic, and for me, well, radiation, yeah, it existed, and stars, where they were just small balls, which I didn't really care about. But now I know how some of their things work, at least, or have some interest. And that was all thanks to you. But there is also me loving this place and feeling like at home, all thanks to the people who are present here, those who are online. Thank you very much. I really appreciate you being around and you being friends with me. It's been amazing place where I found lots of new people, but I also found lots of new four-legged friends. And I have to thank some of the cats and dogs that made friends with me in the Leuven. Those are also very important acquaintances that I made around here. I can go on forever, but I also feel that people will be a bit thirsty, at least I am, and water does not kill my thirst enough. So I will end my long monologue here and invite you to have reception. Again, thank you all for being here, for attending the seminar, and share. Sorry. Now you know how much I want to.
We have a picture with the student and the supervisor and the home.